Now, I know a lot of you are probably very worried at this part in the section. You're saying, Jason, we've had 3 videos with 0 calculus. There have been no integrals. Where are they? They're right here. I've been saving them for you. So this is where we combine the material from all 3 of those videos into a little calculus. And again, there's so many like more places that you can go with centers of mass and moments, but we're not gonna do it. Okay. It would take multiple sections and it's cool, but we don't have time for it. So we're just doing the simples. Simple stuff. Simple's all relative, right? So let's get some introductory material and then we'll show how to find the center of mass of a lamina. Now, first off, what we got to do is say, what the heck is a lamina? All right, so there are a couple definitions of lamina, but when we say lamina, basically what we mean is a thin plate of constant density. And of course, the density doesn't really have to be constant. It could not be constant, and we could find the center of mass that way. We just have a function, something we can't pull out in front of an integral. But here, let's just make it easier on ourselves and say, yeah, constant density. So everything we've done so far has been discrete, right? Not continuous. That's discrete versus continuous is kind of the comparison. Where there were 3 points, right? Here, on this example, there were also 3 points. What if there's infinitely many things that we're looking at for centers of mass? Well, if there's a continuous, actually it can be discrete and infinite, but if, okay, I'm getting on a tangent now, but if the objects are just everywhere, not at precise points, we're going to need some integration. So another definition that we're going to need is a centroid. The geometric center of a lamina, that's not how you spell lamina, is its centroid. So in this case, the center of mass is the centroid. Why? Because if it has constant density, the center of mass will be at the same place as the geometric center. The only time the center of mass is not the same as the geometric center is going to be when the density varies. But here, the density is going to be constant here. So for all intents and purposes in this video, the center of mass is its centroid, the centroid of the region. Okay, so that's basically what we are doing here. One more theorem that we're going to start and introduce that will make our lives easier, called the symmetry principle. And then we'll really get into the calculus of it all. And I'm hoping this theorem is very intuitive. I'm hoping you hear this theorem and you go, well, yeah, duh. I would love that. Okay. This theorem says that if a region R is symmetric about a line, then the centroid is on that line. That line. Right? So visually, let's say we have some kind of parabola. We know a parabola is symmetric about this. So if we were looking at if R was maybe the region right here, what's the centroid of this blue region? I don't know where it is, but I know it has to be along this axis of symmetry. Maybe it's here, maybe it's a little above, maybe it's a little below. But if it's centered on this, again, constant density is important. If it's centered on this, then the center has to be on this, is another way of saying that. Okay, that's a symmetry principle. We can use this a lot of times to make things a lot easier. If I ask you the centroid of a region and you see symmetry, don't do any integration. I'll hold you to that when we do selected homework problems. All right. Something symmetric, you can save yourself some integration. Use the donkey method. Haven't referred to the donkey method for a while. You can save your work. You don't have to use high technology. Okay. Now, where do integrals come into this, you might be asking. Maybe you're not asking. Maybe you might be. I hope my cat doesn't run into my computer right now. I don't usually record videos this late in the day. So they're usually just very sleepy. But it's the evening time. Evening time is cat go crazy time. All right. Let's look at some sort of function. Woohoo! And let's look at the region between A and B. Here, I give you this region or the lamina. Think of this region under the curve as being a thin plate of constant density. That's the lamina that we're talking about here. And if we're curious about the centroid, that's basically the center of mass of this region. So again, just right off the bat, visually, let's see, maybe it's here or something. How do we find it exactly? Well, if there were a discrete number of objects, we could calculate the center of mass using what we did in the last video. So, in the heart and spirit of Calc 2, what are we going to do? Well, if we had a finite number of things, we could calculate it. So let's approximate it. Let's divide this up into a bunch of little pieces. Let's look at just one little piece of this. One little piece is a rectangle. We can find the center of mass of this rectangle. And then we have n rectangles. Can we find the center of mass of n things in two-dimensional space? Heck yes, we can. Woo! And then that'll turn into a Riemann sum. We take the limit as n goes to infinity. We got an infinite number of infinitely tiny things. We can find the center of mass. That right there is a definite integral. And calculus is indeed in this section, not just physics. Okay, I'm getting excited. Let me calm down. So we need to find the center of mass of each one of these pieces. What is the center of mass for the ith piece? Well, this will be the moment with respect to the y-axis of the ith piece divided by the mass of the ith piece. As a side note, there are two subscripts. We usually separate them with commas. So that right there is a comma. And again, the center of mass for the y-coordinate of the ith piece will be the moment about the x-axis for the ith piece, again divided by the mass of that ith piece. Whew. So we don't know the density of this. We just know that it has constant density. Let's call its density rho, just like we did in the last section. Density rho. Very common choice of Greek letter for the density. So let's just find all these things for the ith piece and then add them all up and we'll get it. So let's start with the total mass. All right. What is the mass of the ith piece of this rectangle? Well, remember what density is all about. Density is just the mass per area. Right? So density is mass per area. So if you multiply that by area, you just get mass. Right? Mass is just going to be density times area. We talked about that in the last video. Or density times volume. Depends on what kind of density we're looking at. Here we're looking at two-dimensional density. So it's going to be the density times the area of that ith piece. And what's the area of that? Oh, you know what it is. It's the height of that ith piece times the width of that ith piece. Woohoo! Look at that. We got the makings of a nice little integral. Because if we added up all of these, we get the total mass of the region. And that'd be a definite integral. And I'm getting excited about it. Slow down. No integrals yet. So that's the mass of the ith piece. You know what? I'm not doing. I'm not holding myself back. So the total mass, right, is just the mass of all of these added together. This is a Riemann sum, right? As n goes to infinity, this approaches the integral from a to b of the density. And again, if it wasn't a constant density function, this would just be a rho of x times the function value dx. That is the total mass of this lamina. Well, now let's do the same thing for each moment. All right, the moment, and this might not be what you think it's going to be. I remember getting surprised myself the first time I did it. The first moment with respect to the x-axis of the ith piece of this is going to be what? Okay, so this is where things get a little weird. Let's look at the center of mass of each of these pieces. Okay. And again, the moment, what is the moment? Think back. You can actually use this to find the moment of that piece. If y bar, if the center of mass, y coordinate, is mx divided by m, then the moment is just the mass of that piece times the center of that piece. Now you might think this is going backwards, but it's not. Watch this. Is the mass of the ith piece times the center vertically of that ith piece. But it's a rectangle. It's a rectangle with constant density. The mass of the ith piece, we already got that. Right? It's just rho times f of x sub I times delta x. Well, in this rectangle, what's the y coordinate of the center of mass? It's just half of the function value. Yeah? If we look at this rectangle, what's the center of the rectangle? Half the height. So we can clean this up a little bit, right? This is 1/2 rho times f of x sub I squared delta x. And so that's the moment with respect to the x-axis of the ith piece. So the total moment, the moment of the whole system with respect to the x-axis, is just going to be adding up all those things together. Sum I equals 1 to n of 1/2 times rho times a function value squared times delta x. That's a definite integral too. Woohoo! We get integral from a to b of 1/2 rho times the function value squared dx. It looks bad, but it's not that bad. Can you find the next one? Can you find the moment of the ith piece with respect to the y-axis? It actually doesn't look the same as this. Now we're going to do something very similar. It's going to be the mass of the ith piece times x bar for that piece. Again, just looking at this rectangle, what's the x bar here? Again, we already know the mass. Mass is just rho f of x delta x, like before. But what's the center of this rectangle in terms of x? Well, if this is like xi and this is x sub I plus 1, it's just going to be the average of these two x's. And we can really be as precise or as not precise as we want of that. Actually, let's not undo this. The idea is we can just call it x sub I star. And in fact, we can have this be x sub I star as well. And just say that x sub I star is the midpoint of the ith interval. Because remember, when we construct Riemann sums and say they're integrals, It doesn't actually matter where in the interval we are. So the midpoint works out just well. And if that's the case, then the center, x-wise anyway, the x center of this is just in the midpoint of the interval, which is just that x of I star. So the first moment with respect to the y-axis is the sum of all of these, of rho times the function value at that I star times x. I'm changing the order a little bit. Times delta x. Hey, this is a Riemann sum. So as n goes to infinity, this moment is the integral from a to b of rho times f of x times x dx. And usually it's written with the x in front, actually. Usually written like this. So now we can find the center of mass. We have the moments. We have the total mass. Center of mass, no problem. And that's this theorem. We'll introduce the theorem. We'll introduce an example, and then we'll be done. Woo! So let's do that in the next video.